minister is available, will come back to his opening speech.
Thank you, Arnaud. I will just share my screen. Can you see it well? Yeah. So good morning, everyone. My name is Zakia Adam. I coordinate this program with Arnaud, and it's a pleasure today for me to start this first webinar with you. I'm very happy to share our knowledge and also to learn from you also about Ghana energy sector. But before we dig into modeling and projections, we need to work on statistics. Some of you are professional energy statisticians with already many years of experience. So what we will discuss today may be obvious to some of you, but we will try to bring our broader perspective as the IEA has been working on statistics for nearly 50 years now and with more than 120 countries over the world. It's also important that we all share the same language and have a common base of understanding. So this is the agenda for the training, and today it's the first webinar where we will start with the statistics one, and we will look at the fundamentals and data validation of energy data. Then on Wednesday, we will continue with looking at statistics by commodity. And in total, we will have 4 statistics sessions followed by 6 modeling sessions, out of which 4 will be done by our IEA modelers and 2 will be done by our partners from Imperial College and Polimi. After the modeling sessions, we will have one on the Sustainable Development Goal 7.1, which is on access to clean cooking and electricity. And then we will end up with a quiz and closing. Before we start with the technical part, let us quickly look at some of the housekeeping rules to make our session the most effective. So the entire session is being taken place in a virtual mode, and if you want to ask us any questions, you can use the Q&A box to send us your questions. But if you have an urgent, important clarification, you can use the reaction and raise your hand box. If you have any other questions, please send us emails to Arnaud, me, or to the Africa Program mailbox. This first slide is to show you how data and the modeling work of the IEA has permitted to estimate the impact of COVID-19 crisis on different energy and climate indicators. A first striking discovery is that energy investment decreased in 2020 by more than 18%. And this is almost plunging by around $350 billion. Mostly due to oil and gas investment dropping drastically in the upstream, midstream, and downstream. Another important point is that energy demand, it decreased by more than 5%, which was led by a drop in the use of fossil fuels, especially oil products that witnessed a sharp decrease in its energy demand for transportation, being strongly affected by lockdowns and restricted international travels. This also caused a historical decrease in CO2 emissions, which is a good news, but in order to achieve long-term sustainable goals, the opportunity of the crisis should be used to design recovery plans with strong decarbonization focus. Unfortunately, the recent IEA analysis is showing that in 2021, CO2 emissions will increase quite drastically. However, another good news in 2020 is that renewables emerge as the only area that is able to contrast with this trend. The pandemic has...
Zakia, sorry for interrupting.
Yes.
We have now the Honorable Minister is available now, so we can move back to his
sure.
To his opening remark. Your Excellency, thank you very, very much for your time. We are delighted to have you today to take a few minutes to open this capacity reinforcement program on energy data and energy statistics. and my colleagues and myself are very happy to welcome you today.
Thank you. Sorry for being late. The Attorney General and the Minister of Finance dragged me into another pressing energy matter. So the Executive Director of IEA, participants from participating institutions, ladies and gentlemen, on behalf of His Excellency the President, Nana Addo Dankwa Akufo-Addo, it is a pleasure to join you to launch this online course as Energy Statistics and Modeling, proposed by the International Energy Agency for energy professionals from Ghana. The energy sector, as we all know, plays a critical role in economic development of the country. In order to design and implement strategic energy sector policies to support sustainable socio-economic development, access to energy for all, and climate goals, we need reliable, robust, and timely data. Energy data and statistics enables us to track progress achieved, evaluate performance, and plan for the future. Knowledge in modeling and setting targets on what energy systems should look like in the future. Modeling and planning should be used to prevent future challenges that may occur in the energy sector of the country. The IEA is at the heart of global dialogue on energy, providing authoritative analysis, data, policy recommendation, and real-world solutions to help countries provide secure and sustainable energy for all. The interest expressed by the IEA to support Ghana in reinforcing capacities of both energy statistics and energy modeling is highly welcome, and we thank the European Union for funding such a novel cause. The government of Ghana is very pleased to see the IEA reinforcing its ties with Africa, considering that the continent's weight in global energy markets is increasing and will continue to grow in the next decades. This cooperation will benefit both Ghana and the IEA, a win for both of us. In the past, the Ministry of Energy took part in an important high-level forum organized by the IEA to discuss energy topics. A typical example is the Ministerial Roundtable on Impact of COVID-19 on Africa's energy sector, Challenges and Opportunities, organized 30th June 2020, where my predecessor, John Peter Amewu, the former minister, gave insightful remarks on the impact of the effects of the pandemic on Ghana's oil and gas sector. This training is an excellent opportunity for further collaboration between IEA and Ghana. The participants for this training are Ghanaian energy professionals from the Ministry of Energy, Energy Commission, Volta River Authority, Bui Power Authority, Electricity Company of Ghana, Ghana National Petroleum Corporation, Ghana National Gas Company, Bulk Oil Storage and Transportation, as well as from Ghana Statistical Service, Environmental Protection Energy Agency, and Ghanaian universities. The program has been designed to provide participants with practical skills and knowledge in the development of more accurate and timely statistics, in enriching the use of or update of energy models for planning purposes. In the coming 3 weeks, you will hear from IEA experts who work with countries around the world. I would admonish you to fully participate in all the webinars, ask all your questions, and share the perspective of Ghana with the IEA. I know your views will be of great interest to the IEA. This online training is the first step within the program proposed by the IEA, and we look forward to having the face-to-face training activities in Accra and to meet in person as soon as possible. I hope this will be soon. I declare this training collaboration between Ghana and the International Energy Agency duly launched. Thank you all.
Excellency, on behalf of the International Energy Agency, we'd like to thank you for your remarks and for your very strong support for this training program. We very much appreciate it and look forward to the next few weeks. We know that in Ghana, we will also learn a lot from all of you, and we also see this as a first important step in further developing our close working relationship. One little point I'd like to just mention, we will be organizing our third AUC IEA Ministerial Forum on the 18th of November. This is through our close work with the African Union. We very much hope you will be able to join us there as well. But on behalf of me and my colleagues, we couldn't do this without you and your colleagues at the ministry, and we look forward to the next few weeks of training. Thank you very much, sir.
Thank you. Thank you. And we wish you well.
Thank you very much, Your Excellency. Thanks for your inspiring words to the group of participants. So great that you have launched and kicked off this training course. So now we will directly move to the training itself. So back to you, Zakia and Nicolas, to take the participants through the importance of energy statistics.
Thanks,
and thank you very much to Roberto for your opening remarks, and to you as well, Rebecca, for joining us for the opening of this training.
Thank you. Thank you.
Thank you. So I will share again my screen. So I was saying that the pandemic, it has also had an impact on progress towards the Sustainable Development Goal 7 of reaching universal access to energy. Sub-Saharan Africa is now home to 3/4 of the global population without access to electricity. And the number of people without access to electricity has been decreasing since 2013, sorry. And this is thanks to progress made in several countries such as Kenya, Senegal, Rwanda, and Ghana itself. Still, this progress is being reversed as population without access to electricity, it's set to increase again in 2020. And this is due to several reasons. First, the pandemic, it has forced governments to shift their immediate priorities to purely emergency measures, resulting in a lack of financing available to expanding and improving electricity infrastructure. Then, private companies deploying decentralized energy solutions like solar home systems and mini-grids have faced operational and financial challenges. In addition, the pandemic and its consequences are also affecting populations that are already connected, preventing them from paying for modern energy services. By the end of 2020, up to 30 million people who had access to electricity in sub-Saharan Africa were no longer able to afford to pay for basic electricity services. As a result, in 2020, close to 600 million people live without access to electricity in sub-Saharan Africa. One factor limiting progress is access to finance. Although already very expensive in the region, borrowing is getting even more costly. African countries with the highest needs for progress on access are particularly affected, and this alone could result in 2 million fewer people gaining access to electricity in 2021. The future, it's very concerning. A delayed recovery would see population without access to electricity increase to 630 million in 2030, a time when sub-Saharan Africa will concentrate 85% of global population without access. A similar pattern is being observed also for clean cooking, with population without access growing to 1.1 million by 2030, while in the immediate future, millions of households in rural and peri-rural urban areas are at risk of backsliding from modern fuels to using charcoal, kerosene, or fuel wood. So before we start with the presentation of the the fundamentals, let us quickly do some interactive questions to test a bit your knowledge on energy statistics. So please connect, you can use your phone or your computer to connect to the menti.com website. I will connect myself as well. Wait while I share my screen. So once you connect to www.menti.com, please use the code that appears here. So I don't think I shared the proper screen. I'm sorry. I will share again. Yes, this one. Yeah, this one. So once you connect to www.menti.com, please use the code that appears on screen, which is 88, 41, 30, and 91. So once you connect to the website, they ask you for a code, and the code is 88, 41, 30, 91. And the first question is, what are the units that we use in an energy balance? Do we use physical units such as cubic meters, tons? Do we use energy units such as megajoules, kiloton of oil equivalent, British thermal units? Or do we use financial units such as dollars, euros, or you don't know? There is 4 possible answers. Please reply. What are the units used in an energy balance? Is it physical units, energy units, financial units, or you don't know? I'll give you a few more seconds to reply. We already have 15 participants who have replied. 14 think that it is energy units. So, yes. So we have more than 20 people who have replied, and indeed, I'll give you a few more seconds. I see answers getting in. So yes, the correct answer it's energy units. So in an energy balance, we use energy units such as megajoules, KTOE, British thermal units. You can choose whatever units you would like to use. In commodity balances, which is different from energy balances, there we use physical units. So next question is, what is a calorific value? Is it the quantity of energy contained in a unit of fuel, for example, megajoule per kilogram? Is it the temperature at which a gas changes of phase? Or is it the monetary value or the price of a fuel per unit of energy? So what is the definition of a calorific value? I will wait a bit more for some more participants to reply. So the correct answer here, it's the first one, which most of you got right. So a calorific value, it's the quantity of energy contained in a unit of fuel. And in the presentation, we will look at a calorific value in more details. It's a very important item. Next question is, with which institutions do you cooperate for energy data work? Here it is an open question. You can write down the institutions, ministries, or organizations that you work with for your data work. So we are interested in knowing about this. So write down and let us know which institutions do you cooperate for energy data work. So we have some answers arriving. Energy Commission, NRL, IRENA, Energy Commission. Bulk storage and transport, international oil companies, very interesting. Power producers, Petroleum Commission, Ministry of Energy, ECRI. We have many that have written: Energy Commission, Ministry of Energy, GNPC. Thank you for letting us know with which institutions you work. Now I will start the presentation. So I will share again my screen.
So let's start with discussing the basics, since energy data and statistics are the foundation that gives the ability to understand the entire energy systems. As we all know, energy plays a key role in our economies, societies, and lives. Having reliable and high-quality data and statistics has always been a concern in the statistical community. Still, several decades ago, quality was not as good as today, and there were inconsistencies in the methodologies used. Many organizations were not using the exact same definition and scopes, so there was a need for harmonization for a common framework establishing standards. Today, the framework exists. It is the IRIS. It enables us to speak the same language. It is a comprehensive framework on the scope of energy statistics, classifications, units, methods, data collection, institutional arrangements, quality assurance, and dissemination. The IRIS has been approved by international organizations. In the early 2000s, the IEA undertook an initiative to organize a group, the Inter-ENERSTAT, composed of various regional and specialized agencies active in energy statistics. This group acts as the secretariat for the IRIS under the UNSD. It provides comparability of production, transformation, and demand flows over all products. The IRIS has been adopted by most international organizations, including in the African continent, the AFREC, and the West African Economic and Monetary Union. As having reliable and harmonized data is key for analysis and decision-making, we advise all countries to refer to the IRIS for their statistics. How do we structure energy data to get a picture of a given region or country? The key split is supply and demand. In the supply side, first you have the production in the country and from other sources. Then you add imports and you extract exports. You can consider international bunkers. There are several methodologies for this, and stock variations. As you can see, for stocks, you have arrows in both ways. Stock levels are a very important indicator in data analysis. On the demand side, you have first the consumption by the energy sector itself and for transformation. For example, for refinery, you have the transformation that is converting crude oil into gasoline. You also have the industry own use processes like the steam crackers to create heat. Second, you have the consumption by end use sector broken down by industry, transport, residential, commercial, agriculture, non-energy use, and many more. The two sides normally should match, but in reality they don't, and that's why we have statistical difference. Statistical differences can show the data quality and therefore is a very useful indicator. So statistical differences can have a meaning by themselves. This breakdown by supply and demand work for several levels, at a country level, but also at aggregated regional levels. In which units shall we treat energy data? We need to agree on a common language. We all know many energy units. If in volumes, there are liters, cubic meters, barrels. In mass, there is grams, tons, pounds. And in energy units, you have the ton of oil equivalents, ton of coal equivalents, you have joules, watts. So we need to express information in energy units, and to do so, we have to convert from physical units to energy units using a conversion factor, which is the calorific value. The calorific values represent the heat obtained when the fuel is combusted. It is an indication of the quality of the fuel. The higher the calorific value, the higher the energy contained by unit of volume per weight. Therefore, it is useful to understand the quantity of energy. If you want to generate as much energy as possible, and I ask you to choose between 1 cubic meter of wood, 1 liter of oil, and 1 ton of coal, you need to know the calorific value to make the best selection. So calorific values have variations, and it varies among fuels and within the same product depending on the quality. See here the example of Morocco and South Africa, where you have the same product, which is bituminous coal, but with different calorific values depending on the quality. So whenever you collect energy data which is usually in physical units, you need to also collect the associated calorific value. It is even more complex as there are 2 different calorific values, which is the net calorific value and the gross calorific values. When you burn a fuel, you get the useful heat and water vapor that is not recoverable. Gross calorific values includes both, that is the energy of the fuel and the energy in water vapor coming from the humidity in the fuel when it is combusted. Whereas the net calorific values, it includes only the useful energy. Therefore, gross calorific values is always higher than the net calorific value. When a calorific value is reported, it is important to also ask whether this is on a net calorific value or gross calorific value basis. From one, you can calculate the other with standard ratios. Now, let us look at an example. When a country reports its energy data, it is usual to give 1 unique number for the physical quantity and 1 unique number for the calorific values. Here, let's take the example of a country with 2 fields of gas. Each field has a different calorific value and produces different quantities of gas. When you compute the total gas production, what calorific value will you use? In this case, we have to report the weighted average calorific value because it will take into account first the weight of each source of gas, and second, it will provide us a better estimate of energy supply and demand figures. Wrong net calorific values could bring to statistical differences, over-reporting or under-reporting in energy units. Now we know that energy data will be reported in energy units. Let's see how to present all the energy data of a country. At the IEA, we use an energy balance. In the energy balance, all the flows and energies are represented in a single table, and everything is reported in a unique unit, which is the KTOE, kiloton of oil equivalent. You can choose another unit, but you just need to specify it. The energy balance is structured as such. First, in the rows, we have the flows, which is first on the top part, you have the supply. Then you have the demand, which includes the energy sector own use by a refinery. For example, you have the transformation, for example, from gas to electricity, from crude oil to oil products, and you have the end use consumption. In the columns, there are fuels and energies, and given that we are reporting everything in the same unit, you have on the right the total column. All this is very useful because all the energy data of a country are included in a table, and you can easily see the key information such as what is the first fuel in the energy mix in terms of supply, what is the first source of energy to generate electricity, which sector consumes the most energy. You can also compute sophisticated indicators such as energy self-sufficiency. Now that we are all clear on the basics, let us discuss more the process of collecting data in a given country. Here we present generalities. Everything might not apply to your country's context, but it comes from our experience of working with several countries. In view of the role and importance of energy statistics, one would expect basic energy information to be available in a reliable and timely way, but it is not that easy. If we want to have detailed and reliable energy data, it is helpful to have an entire ecosystem and set of enabling conditions. First, we need to have a collection system, and this includes several pillars. A legal basis with statistical laws and other national laws and regulations where reporting of energy data would be mandatory. The legal framework creates a necessary foundation, but it is not sufficient for energy statistics. We need to establish institutional arrangements to ensure collection and compilation of energy statistics in the most efficient way among all the relevant members of the energy statistics system. Another pillar of the system is a proper reporting and dissemination mechanism, which means questionnaires compatible with international standards, a network of contacts, and a data release calendar. It's better to work on data collection when you know for what publication you're getting the data and when it will be released. We also need to review the methodology, anticipate and adapt to changes and new challenges to meet national and international needs. For example, it is now more important to focus on new renewables and their full contribution to the energy system than in the past because of their particular challenges and their growth. Collecting any statistics has a cost. However, lack of data quality could lead to even higher cost, and there should be a balance between the efficient use of resources and collecting what is necessary. What is necessary will depend on the needs of data users. However, not all needs will be possible to meet. It is important to look at the changes in the energy sector and to limit the collection by cooperating between the relevant government agencies. Cost is one challenge, but there are others. There are challenges of specific trends or new type of energy activities. For example, biomass data collection is very challenging. Off-grid data is a new trend. the liberalization of the energy markets, which has two major impacts on statistics. First, while in the past we could obtain detailed information from a single national company, now many surveys are required to have a comprehensive view of a sector. Secondly, a competitive market often leads to confidentiality issues that add to the difficulty of collecting basic information. Other challenges are lack of resources and also the forced turnover of staffs. The process has several steps. We have to collect data, verify them, process data, and then disseminate them. Here we illustrate the data chain of energy statistics. Let's imagine a real activity. In a gas field, we extract gas, which is production. It is sent to the power plant, which is a transformation. And then we use the electricity for powering air conditioner equipment, drive an electric vehicle, and this is the end-use consumption of electricity. The data for all of these activities needs to be collected, and this step is called primary data collection. This is where you might be involved. That is, discussing with the utility that reports the quantity of gas used for power generation, conducting the surveys to households to understand how many air conditioners they have, looking for information on the consumption and efficiency of an air conditioner, etc. Then national administrations submit these data to international organizations in a certain standard format. For the IEA, it is mainly the energy balances. These data will be consolidated with others of other regions and compared to previous years. Once enhanced data are available, they can be used by first governments to shape energy policies, for example, to support electric two three-wheelers or energy efficiency standards for air conditioners. Then it can be used by the private sector and investors. And it can also be used by the civil society. NGOs can look at the CO2 emissions and call for more policies to reduce energy-related CO2 emissions. Who are the players involved? In terms of players involved in energy statistics, one of the most important one is the Energy Ministry, which sets policies of the country, and the other one is the Statistics Office, which is usually in charge of statistical compilation within the country. Usually some processes exist between the two for sharing data. The ecosystem is made of many other stakeholders, which are all very important, and collaboration between them is key. Energy regulators might have a lot of data, but they would have an incomplete view of the supply side without trade data. This is true for imports of fuels, but can also be interesting for off-grid solar systems or solar panels. Information on the demand side will also be incomplete without some form of comprehensive surveys. Ministry of Transport may have data on cars and trucks that will complete your understanding of energy statistics. The Statistical Office and Energy Ministry can then hold large amounts of data, but further collaboration is needed to make sure that appropriate outputs are disseminated and used accordingly, and that the right institutions are involved at each stage. What tools can be used for getting data? There are several possible sources, such as administrative sources. You need to check first before starting, because maybe some data are already available. The second one are surveys. It's quite challenging because, and we need to be careful when we do sampling. The advantage of surveys is that you can, if you have existing surveys, you can just add a question. Example, asking a question on source of lighting, fuel for cooking during a demographic and health survey. Metering. Metering is very relevant for energy infrastructures, energy transformation, and for industrial consumers, but it is costly. Another tool is modeling. We do not mean to make projections and forecasts. What we mean is that we can estimate historical data based on proxies. For example, in 2018, you have a survey that gives energy consumption of household. You can define a proxy based on incomes and calculate for previous years if you know how this proxy has evolved. One important point is statistical confidentiality. Confidentiality should be taken very seriously. It is necessary to prevent unlawful disclosure of confidential data. But in some cases, confidentiality can be used as an excuse for not disseminating data. Solutions can be found in order to have more published data. And so a dialogue between the government and the private sector is needed in order to ensure that the data becomes accessible and treated without negative consequences for the company providing them.
So now we will pause for questions and answers. I have been joined by my colleague Nicolas Cohen, who is an expert on energy statistics and who has been processing many African countries. So please send your question and answers in the Q&A box and we will answer them. I see there is already one in the box. So Nicolas, if you want to answer this one.
Well, I kept it. It was asked quite some time ago by Joseph. Thank you for your questions. So it is letting some time for the other participant to ask if they have some questions or comments. So how do you estimate the population without access to electricity as well as clean cooking? Is it based on number of persons per population, or if so, why not per household? So yes, thank you. We will have a dedicated session regarding access to electricity in the later part of the training. For now, I'm not the one that in the team working on that, but we are mostly working with official figures from either the government, so energy ministries around the world, or from some energy electricity providers that can publish sometimes their statistics on the number of either clients or households provided with electricity. So for methodology, we use a percentage of the population, so number of people with access to electricity. This is because mostly commodity and methodology, but also in terms of logic, it's more interesting as the human development indicators to see that a person has access to electricity rather than just a household, because it's, say, a generic image. If you have only one electric plug for a house, it doesn't mean that everybody in that house can use the electricity as they would like to. So that's just an image to say why we use the number of people instead of the number of households. And yes, as I told you, we will have a specific and dedicated session regarding this subject and modelization of it to see a little bit more in depth how we work on that. So even Jose Agbo, in case there is no data available, for example, appliance electricity consumption for rural and urban households, can you extrapolate from similar countries? If yet, what's the best way to do it? Thank you very much. So we are getting already in the hard part of the work as an energy statistician. So indeed, sometimes you might lack energy data. At our level right now, talking about energy balances, we do not have the detail on appliance for electricity consumption or rural or urban household. For now, when we talk about energy balances, it's mostly the domestic residential consumption or the industrial or some other, say, generic sectors of the economy. Nevertheless, even for those more generic sectors, you can have difficulties to collect the data. And indeed, it can be sometimes one of the tools that we can use is to find another country with a similar level, let's say, of the economy, so similar GDP and industrial structure, which is not always the case. And in that case, you can apply a share of the total electricity consumptions to some specific sectors. This is nevertheless an estimation, and it's always better to try to work with your Office of Statistics or the Energy Ministry to try to develop some tools to capture those data, because estimation can help for 1 year or to help correct one data point, but it's not good if you have both elements that repeat on every publication and you keep going on those estimations because they would not match the reality. I don't see any other questions right now.
Yeah. So please send your questions before we move to the last part of the presentation on data validation. I don't see any more questions, so maybe we can continue, and we will have another question and answer session at the end of the presentation as well. So in the meantime, if you think of something, just write it in the Q&A box. Before we continue with the presentation, let's do again some interaction with Menti. So I will share again my screen for Menti. So here, please connect to www.menti.com and use the code below. Which is 88, 41, 30, and 91. I hope you can see my screen. And the first question is, what are the types of checks you can apply to energy data to ensure quality? So please connect to www.menti.com and use the code 88, 41, 30, and 91. So this is an open-ended question. You can write down the type of checks that you do when you're checking your data. Give you some time to think about it. So a few answers are coming. Historical checks. So yes, it's good to check for the time series and see if there are big jumps, outliers, if it's justified with some specific economic situation. Statistical difference, indeed. The units, yes. Outliers, integrity, analysis, trend analysis, yes. Give you a few more seconds if you want to write down the type of checks that we can apply to energy data to check for quality. Yeah, scatter plot, yes, to see if there are some which are out of scale. Trend analysis, yeah. Robust verification system, indeed. Data comparison, yes, you can compare different data sources. So excellent. Let's do the second question, which is, how can you verify the fuel consumed, which is the input, and the electricity produced, which is the output, by a thermal power plant? How can you check for the fuel consumed and the electricity produced by a thermal power plant? Can you do this check by analyzing the trend of production in the past years, depending on technology, or you can compare the ratio of output input with expected efficiencies by technology and sources, comparing the level of outputs production with similar countries. So here, which one of these is a way to verify that your inputs and output are correct? Give you some time. We see answers are coming. Everyone is saying it's by comparing the ratio of output to input with expected efficiencies. And indeed, that was the correct answer. So excellent, everyone. Bravo. Last question. So what do you think is the efficiency of a traditional earth kiln to produce charcoal? Is it around 80%? Is it around 40%? Is it around 20%? So what do you think is the efficiency of a traditional earth kiln to produce charcoal? Try to guess the efficiency. So we see that people are hesitating between around 40 or around 20. We have one, but so it's really equal, 50-50, around 40 and around 20. Give you some more seconds if other people want to reply. And the correct answer is, for a traditional earth kiln, it's more close to 20%, but you have some improved earth kiln that can go to around 40, but the traditional one, it's more close to 20%. So thank you for participating. So now we will move to the presentation again. So we will do the last part, which is about data validation.
Let's start with a summary of the recommendations to establish an energy information system. One should establish a solid legal foundation. Also, it is important to ensure institutional arrangements, to build up formal procedures to support confidentiality, and to establish a data collection strategy. One should also provide up-to-date metadata and follow the international standards and concepts. Let's now have a look in more details at the data collection strategy. First, to establish an energy data collection strategy, one should identify data needs, both on the national, on the regional, and on the international scale. Then, one should look at the data that is already collected by NSOs, by other ministries, by other public actors, private actors, and by international agencies. Once these are compared, we will be able to identify data gaps, which are the data needs that are not yet collected with the proper requirement levels. That could be on frequency, on level of detail, on definition, etc. Then it is possible to establish a strategy to collect the required data and include it in the national data strategy. This should include a legal framework, the allocation of resources, and the procedures for data collection and validation. And this is what we will have a look at now, the data validation. Data validation is important to ensure good data quality. And data quality is defined with 5 main aspects. First, relevance. The statistics should meet the needs of the users. Then they should be accurately and reliably portraying reality. They should be released in a timely and punctual manner and be consistent internally over time and comparable between regions and countries. And last but not least, they should be presented in a clear and understandable form, released in a suitable and convenient manner, and available and accessible on an impartial basis with supporting metadata and guidance. And for more information, you can see the links below. How to ensure data quality? We need to do different data validation steps. And the first thing to do is to check the internal consistency. Things to look out for are if one field is supposed to be the sum of 2 others, is it? Does the detailed breakdown match the total? Are stock changes correctly calculated? Is the dataset complete? Is the decrease in use of one fuel coupled with an increase in use of another one? Or can you explain it with other reasons like efficiency improvements? And is the story logical? Then it is also good practice to analyze the data validation processes to identify possible points of failure and introduce checks. An example with this process A. Process A requires extracting fields, summarizing data, and reformatting data sets. It is easily happening that 1 or 2 items are dropped from the large data set. Because of this, one should compare before and after counts and the totals of data. One other aspect are the statistical differences. Indeed, when we collect energy data, we try to get a picture of supply and demand in a market. And in economic theory, we would expect that with an equilibrium, supply is equal to demand. The supply is how much is available to the internal market. The demand is how much was consumed in this market. In practice, as measuring supply and demand comes with challenges, and often we have different sources for the both sides, there can be a difference, which is the statistical difference, the difference between supply and demand. And this statistical difference can help us validate the data. Indeed, high statistical differences can be a red flag, often when it's more than 5% of the deliveries to the market. But we say that a statistical difference of 0 can also be suspicious, as it might mean that it was hidden in one of the commodity balances flows. So what can I do if an issue arises with a statistical difference? One should check the completeness and coverage of the data, check if there is double counting. One could have a review of the definitions and methods of data sources, check calorific values for supply and demand, and check if there are any new trends missing in the dataset. A specific example to verify electricity statistics is to verify the on-use and the transmission and distribution losses. First of all, the on-use. On-use of electricity by power plants as a proportion of production is not expected to vary significantly year on year. So this is something, when we map it over the time series, that we can use to validate the data. Similarly, transmission and distribution losses should not go above 10%, at least the technical transmission and distribution losses. However, it can happen that with bad maintenance of the grid or theft, we have higher transmission and distribution losses. We can see it in the graph on the right side. Several regions around the world are higher than 10%. It is just important to be able to explain these differences and potential changes from one year to the other. Calorific values are not only important to the energy balance construction, but they also allow us to check and validate the data. Indeed, for every energy product, there is an expected range for the calorific values. And that's why we will be able to compare the collected calorific values against default calorific values. We can also compare them with historical calorific values for the product because they can be region specific. And last but not least, one should check if the NCVs and GCVs used for consumption are in line with the ones used for supply, because this might lead to statistical differences. Another element that can help for data validation is the growth rate. This involves comparing the data point of the latest period to that of the preceding periods. And this is the formula. And if there is a high growth rate, one should be able to explain it by real-life facts. When seasonality is strong, or we are dealing with monthly data, it is often more useful to compare the current months with the same months of the previous year. And in general, this strategy is very useful for production and consumption, but less useful for stocks and trade. Breaks in time series can happen. You can see two examples on the right side in the graphs. However, we want to aim for a consistent time series. And if there is a break in time series, we want to be explaining it and to avoid unexplained breaks in the time series. Breaks in stocks are rare and should be investigated. And in general, certain flows are consistent over time, where then a sudden increase or decrease will raise a red flag. One example is the refinery intake graph on the right side on the bottom. Here you see that for 1 month, April 2005, we have a very small refinery intake. And for 1 month in December 2005, we have a very high refinery intake. While the first break in time series can be explained by maintenance, for example, the other one is more difficult to explain. And this is something that one should check because usually refinery intakes stay quite constant at constant levels over time. Now let's have a look at transformation efficiencies. These can also help validate the data by looking at the relations between the input and the output. Indeed, for every energy transformation process, there is an input and an output, and there is a relationship between these two that will depend on the technology used. The efficiency will be calculated by the total useful output in net energy units divided by the total input in net energy units. For an example here, you have two inputs A and B and one output C. The efficiency will be calculated as C over A plus B, whereby the inputs and outputs need to be both in the same energy unit and in the same energy form. This efficiency then needs to be checked against the expected ranges for that process and technology. An efficiency larger than 100% is implausible, so that would be a first red flag. And then we will expect efficiencies to be within a certain range depending on the type of plant and the fuel used. They can also vary widely depending on the state of technology. A very old power plant will be less efficient than a very new one. And in general, efficiencies do not vary significantly from year to year as technology upgrades are time and capital intensive. Here is an example of the expected efficiency range, but this is very much country and technology dependent. So don't worry if you have an efficiency outside the range. It's just good to double check and to see if you can explain this difference. Another element to verify the data is to check if the data set is coherent. Are we able to explain trends in data sets? To do that, we can verify the data is coherent with certain related trends. For an example, we have here in sub-Saharan Africa the increase to access to electricity. And this is also visible in the increasing electricity generation. So here the two data sets are coherent. Then certain patterns may also be fuel specific. For example, natural gas demand and storage is linked to weather patterns. Hydroelectricity production is affected by rainfall, etc. Then one should also check if the data match related data collected through different sources. For example, the input to electricity production from electric utilities should match the fuel use and power by other sources. And in most cases, there are relationships among variables, such as the efficiency that we have talked about, that have to be satisfied. For example, if the inputs to power production are increasing, we expect that the outputs will increase as well. And a decrease in input without fall in output can be the result of improved efficiency. And this is the case on the right side for the gas power plants in sub-Saharan Africa. We had in 2000 an efficiency of 30%, and at the end of the time series in 2017, we have 40%. So this explains the difference between the evolution of the input and the output, the electricity production. Another data verification is to check the coherence with economic data. GDP and population data can serve as indicators of data consistency. One can check if the GDP or population is growing steadily and if the energy consumption data makes sense in light of this. Long-term demand trends can also decouple from population or GDP because of efficiency or increased access. But here again, it is important to verify that the story is logical and that you are able to explain trends with real-time events. An example is here the total primary energy supply in the IEA. We see a dip in 2008-2009 in this total primary energy supply. And when we look at the gross domestic product in the IEA countries, we see the same dip. This is actually because there was an economic crisis. And so we are able to correlate one data set with the other one and to explain through economic data. Then it is important to have a look at different data sets and reconcile them when there is a different product classification. Because in general, goods can be classified using three systems: the harmonized system, HS, the standard international energy product classification, and the central product classification. And differences in product classification can quickly lead to discrepancies in data. For example, sometimes fuels with similar qualities can be named differently onshore and offshore, and categories do not always match. For example, biodiesel in the harmonized system can include up to 70% of oil from fossil origin. So this is important to note, and if you have two data sets and have difficulties reconciling them, think about the fact that there might be a difference in product classification. Then you can also try and reconcile different data sources by mirroring checks. This is particularly useful for data sets with a bilateral component, for example, for trade. This helps ensure the consistent interpretation and application of methodology and avoids double counting or missing flows. The goal should be to limit, justify, and explain discrepancies when existing, and it's important to work with partner countries to investigate. The IEA can help you with this. An example on the right side in the graph with electricity trade. Here we see the electricity trade reported on the one side from country A, from country A to B, and on the other side in red, as reported by country B. We see that they were quite consistent along the time, and then around 2013, something happened, and there was a big discrepancy between what both reported. So this is something where we would go back to the country and ask. Discrepancies can arise when we deal with trade data because of different methodologies, for example, physical flows versus contractual flows, or the country of origin destination might be changing. Then there can also be a problem with timing, and different countries may have different definitions. That's why detailed and transparent metadata is essential. Then we can also verify coherence when using monthly and quarterly data as an extra to the annual data. Indeed, Good quality monthly data can be a tool for data validation as well as is key for energy security purposes. We see here on the example for LPG across the years that the monthly data had always been quite consistent with the annual data, except in 2016. So something to look out for are revisions and different definitions or coverage due to timing constraints. Again, in the example, the monthly data was always a little bit lower than the annual data, which points to different coverage, maybe timing constraints, because it's easier to have all the data for the annual, which is later on than for the monthly. However, in 2016, something happened because we have a much bigger discrepancy. So that would be something to query. Last but not least, if countries are not in a position to meet the accuracy and timeliness requirements, they can produce provisional estimates. However, note that these are based on less comprehensive data content. So what to consider? It is preferable, of course, that almost all data are real observed data. Estimates should only be used for flows and products that represent a small proportion of the balance. And they should only be used for a short time whilst a system of data collection is being established. Strategies will depend on whether the data needs to be systematically estimated or if it's only missing exceptionally and you know that it will be provided later on. Whenever a data point is estimated, this should be clearly marked and defined in the metadata. In general, we will ask the following questions when we estimate data. Is someone else already collecting this data or related data? This would avoid the time needed for the estimation. How important is the flow or product? This will tell you how much resources one can put into the estimation. Is it correlated with another flow for which there is data, which could help you to derive the data from that flow? Is there a seasonal or historical trend that can be used for the estimation? Why may this period be different? For example, have a look at the heating degree days for space heating. Can market trends be used as an indication or input for estimation? Last but not least, we will describe how the data validation processes are done at the IEA. An overview of how the data is processed and validated at the IEA is first, we will receive the data. Then we will process it, look at the inconsistencies such as the breaks in stocks, negative values, errors in sum, etc. Then we will do some time series checks, consistency, balance checks, seasonality and outliers, calorific values, and iterate with our data providers on these two types of checks. If we receive new data, we reprocess and we recheck the time series. Then we will have some more checking and peer review where outliers and seasonality will be checked again, and then the database is frozen. And finally, we will disseminate our data. If you want to learn more about energy statistics, we have produced a comprehensive energy statistics manual that covers most of our data collection methodologies, and it is consistent with the IRIS framework. It is available in 10 languages, and you can download it free of charge. Furthermore, we have talked about it already, the international recommendations for energy statistics are available on the United Nations website. And we have also some manuals for indicators and policymaking that are available on our website. The IEA data products include data services for purchase, but also free products on our website, including the Keyword Energy Statistics, a data browser for data and statistics, the energy balance flows in form of Sankey diagrams, etc., etc. I invite you to have a look at our website. Thank you very much.
So now, if you have any questions, please drop it in the Q&A box. I think we had a participant who had raised his hand. Mr. Elliot Ansar, do you have a question for us? I'm allowing you to take the floor in case you have any questions. No? We have some time left, so if you have any questions for Nicola and I, don't hesitate. Otherwise, for the next session on Wednesday, where we will talk about energy commodities, so we will go on each fuel in detail. There will be an exercise session at the end. So if you have time before the training on Wednesday to take a look and practice them, it will be great, so that then during the session when we will look at only at the solutions together. No questions, don't be shy. Well, does it mean that we have been very clear and you understood everything? Again, you already have access to all the presentations on the Google Drive. So normally you have received it by email, the link to the drive. If you have not, you can contact me or Arnaud, and we will share it again with you. Same for the handbook with the exercises and the solutions. You have also received it by email. But if not, get back to us. No question? Well, if there's no question, well, I think we are done for today. Thank you very much for listening, and I hope that it has been useful to you, this first statistics session on the fundamentals and data validation. And I wish you all a good afternoon, and see you all on Wednesday at 9 a.m. Accra time. Bye.